Anyway, so here you will see that there's going to be one expect tutorial and also one PyExpect example of how to deal with expect in a Python environment. I will send you a full cookbook for using PyExpect. It is fairly easy and the syntax is very similar to expect, but for today's tutorial, at least in the first part of the afternoon session, we will start with the expect tutorial. I will you've already some of these steps off, but just to quickly summarize, when you first load your expect in your terminal, you will basically have no settings applied on it. Some things are by default. For example, you can define your statistics. Statistic chi is defined by itself. However, if you want to run long spectral fits, sometimes your model is going to be too complicated in terms of the number of parameters, and your spectrum is going to be having a lot of features, then sometimes your fits can take way longer than the example that we're going to have today. So what's going to happen is that it will start finding the minimum. The fit will start finding the minimum, but it will run into a number of iterations that is set by default by the expect algorithm. So and it will start asking you, do you want me to continue? And instead of just clicking off, yes, and hitting enter all the time, you can just set it by saying query y. So whenever it reaches the limit of number of iterations within your fit, it will, instead of asking you, it will just continue until it's done. So this is also to display your either spectrum, output, your fit results, whichever you want to see. Here you will be seeing how to load spectra if you have more than one. So if you have, for example, for XMM Newton, most of the times you will have 3 different spectra. One approach you can use is to combine them. There's a specific easy command line in the how to use SAS cookbook in one of the links that I also have on the tutorials. But instead, I would rather suggest to have all of them loaded all together and then account for differences in all of these 3 instruments by applying a certain model. So here you will start defining your model 1-to-1, 2-to-2, and then you can keep going like this until you are basically done with defining your data. Whatever you want to do to your data, you need to specify which data set you want to apply it to. So for example, ignoring certain energies or certain, energy ranges that you want to have either for one of your spectrum, but you don't want to do it for the another one, this will be labeled as this, and be careful that there shouldn't be any space in between. So this is basically to allow and prepare your data for any further fitting. You can plot your data and take a look. It is usually helpful to take a look at your data to see, okay, do you really have the correct spectrum? Or if you want to see if there are certain very strong features in your spectrum that you want to know from the very beginning, then it's better to load it in the logarithmic scale. If you load it in logarithmic scale, you will be able to see smaller changes than if you would just load it normally. Then you can continue with defining your model. This structure is very common. So in the first part, you have your absorption column, which describes the absorption column along the line of sight towards the source, which is basically dominated by our galaxy. And then this means that this multiplies both of the components. So this is a simple multiplication that it means that it's both applied on the disk component, which means both the disk and the power law component is going to be convolved with the same absorption as you receive the light in your instrument, which makes sense. Sometimes you will have very, very low spatial resolution, for example, with XMM Newton. Sometimes you will not be able to resolve each specific source differently. Then you will need to have different components to account for each source. But for our case right now, we will not be, we do not have to worry about it. If you want to change one value of your parameter, then you will say, you will type new par, the number, the number of your parameter, the value you want to enter, and -1 means you fix it. You can basically, if the parameter is fixed, you can say, okay, I want it to be free, and then you say, so, all right, so parameter number, and then you go with your own fitting. And if you want to link for two parameters, there's going to be instances, for example, the disk plus NTH comp model, which is another power law model. And both of them will have a disk temperature. So this temperature here is actually the temperature of the seed photons that are coming from the accretion disk. And this is exactly the same temperature that is emitted from the accretion disk. So by logic, it's better to have one parameter, otherwise your fit will start looking for two different ones. And if your spectra are not really that good quality, then you will end up with two different parameters, which will not make any sense. Sometimes you will be lucky and then your model will be able to find similar values, but it's better to have one value across the two components. This is done by saying new par. So in NTH comp, this will correspond to the sixth parameter, and then this BB, this will correspond to the second parameter. Once you're done with your parameter setup, you will start to fit. Once your fit is done, it's better to run the error comment. As I said, I kept repeating multiple times throughout the workshop this week. XSpec will struggle with finding the global minimum. So it will, start exploring the parameter space, and it will find a local minimum, and it might say, oh, okay, this is the minimum that I'm looking for, and it will not go any further in terms of exploring the parameter space. Once you run the error parameter, it will start from the bigger picture, and it will actually continue searching for your global minimum. So it's better to run error on almost all of the parameters, except if you know that some parameters are not going to be well constrained, then you can basically skip them or fix them to a certain value that it might be that value, but it's always a good practice to run error comment. Once you're also done with this, you can see your fit, and in terms of the reduced chi-square value, you can also plot your best fit model, your data, and specific residuals that you want to take a look at. You have two data options that you can plot. One is the normal scale, and the other one is the logarithmic scale. You can also have your data or spectra plotted unfolded, which means that it's going to be not let's say processed by your response matrix. So you will see the spectrum as it is. You can also plot your spectra, the residuals from your fitting in terms of residuals, ratio, which means data over model, then your chi values and your del chi values. The last two are specifically important if you want to take a look at if you actually have any align features. So these, taking a look at residuals after looking at your reduced chi-square value is always a good practice to make sure that you are not missing any components. So here are some examples to do that. You can also modify the limits on your axes. And as I said, after looking at your residuals, you can see if there's an emission line or if there's an absorption line, then you can work with adding more and more components to your model. There's one quick warning when it comes to this, but I will repeat it when we go through the model fitting with our own spectra. Once you are done and you are happy, or you want to take a break and continue with your fitting later on, you can say save, and you will have three options in which you can also all save your model, the parameter values, fit statistic of your model, and the data all together by giving it a file name. You can only save the model, which will save just the best fit model with the parameter values. And then you can only save files. This is going to be useful when you need to work with multiple files at the same time, so that you can just basically load the files that way and then work around your model or whatever you want to do. And once you want to start another session using the settings that you have saved before, you basically just put an @ and run this file as you wish. There are also a few other options that you can modify your plot with. You can play around with the colors, you can play around with your labels, you can play around with the position of your labels, etc., etc. So these are very easy to do, but sometimes it's very easy to mess up as well. So I'm going to be switching to the desktop to share the screen so we can actually work with. Wait a second. Okay. Give me a second. So now you're looking at my desktop, in which I have all of these files saved. I will open terminal over here and start the expect session. So for this specific purpose, I already have a model saved, and I will quickly just make sure that we're working with the same data set. So your spectrum will look more or less like this. If you load both your XMM Newton spectrum and your RXTE spectrum. In this case, your second spectrum will be colored starting from red, and your XMM Newton spectrum will be colored in black. I will quickly look at my parameters. This is a simple disk model that I applied. So here you will see a model that looks like this. You can easily start applying this model to your own model on spectrum as well. There's this dust component, so you can basically skip this first, or maybe I can just actually start typing the model to you, and it will be much more obvious why we will add these components to our spectra. So first I will start clearing the model, and my first attempt is going to be to use the model that we have on the tutorial. If you wanna, so this will prompt you an interactive thing so that you can enter the parameter values if you know them for sure. But if you don't know and you don't want to keep hitting enter, you can basically just do this and it will show you your current chi-squared and your degrees of freedom, which is not really the result of any fit right now. And it will say current data and model are not fit yet. So now you see your model listed for your data group 1 and your data group 2. By default, it will assume that you will have one continuous model, the total model across all of your spectrum. But as you can also see that there are certain flux differences between RXTE and XMM Newton, which arise from both instrumental limitations at certain energies. As you've seen from RXTE, when you load the spectrum, you will see larger energy bins at lower energies and smaller energy bins at higher energies, which means that your spectrum will be much more sensitive at higher energy levels rather than your lower energy levels. It is quite similar in here as well, but the energy resolution is much, much better than compared to RXTE. You will also see the huge contribution from dominantly the accretion disk. So RXTE provides a very nice approximation to the harder energy tail of your spectrum, but you are missing a huge chunk of your information that is provided by the accretion disk. So what you actually end up relying on with RXTE is that how well you can manage to fit this part of the spectrum, which gives you like, I don't know how many, less than 10 bins, let's say, and then try to model the rest of it. So it's better to always try to find simultaneous observations if you want to, for example, constrain your black hole spin, let's say, and you will also see that at higher energies, XMM Newton is not going to be enough just to constrain your power law contribution, because as you will see that the error bars on the counts are much, much larger than what RXTE is showing. So that's why I also wanted to show you how to deal with these things. So to account for these differences between the two instruments and also the observing time, etc., you will need to add a component that is called constant. Sorry. So for your first data set, you will need to fix it at 1, and then you will free it for your second data set. Which this is done by, okay, let's say giving a value at the beginning means that I am assuming both instruments are very, very similar, and both observations are going to be very similar by nature. So the starting point will be 1, and 0.1 or anything other than actually -1 means that it's a free parameter. So now you can also see these when you hit enter. So your constant for data 1 is basically 1, and your data 2 is set at 1. So the fit will start searching for the value from the value 1. So you can actually, whenever you know that a parameter has to take one certain value, but your fit is showing something completely different, then you can basically say, okay, start the fit from this value and then see what you can find. So I don't remember if I actually did this, but for the first part, I will quickly start the fit. And please feel free to interrupt me at any point that you don't understand something, that there's something very wrong, or you are stuck with your fit. But I will either way continue this way, assuming that everything is fine. So now the fit is done. You can see.
May I just quickly, how did you add the component? I didn't catch it.
So it's done as this. So, okay, I can also explain how to add the components into what part. So if you know your component is not a convolution model, which means a multiplicative model like this constant or TBFs, you will need to add it within here. So you have to be careful which model component that you are numbering. So if you want to add another component somewhere over here, you will say 4. So this will mean there's going to be a fourth component between disk BB and power law that will be subject to the multiplicative models, constant and TBFs with all together within one model. Then you will type the name of your component, let's say Gaussian line, which I will also show in a few minutes. For constant or multiplicative models, the order is not really that different. It's basically simple multiplication. So it's as the same as multiplying 2 by 3 and multiplying 3 by 2. So it's the same. So I will plot my residuals. And you will see something very similar to this. As we discussed previously, that there is this one absorption that is present for your XMM Newton spectrum. But as you can also see that it is slightly present with RXTE as well. So RXTE is not really as bad as of an instrument as it seems. However, as in the previous years, before we started, or people started applying different methods to account for instrumental uncertainties, these error bars would have been much, much larger. You can actually test this by yourself by not applying a PCA correction tool and just adding 1% uncertainty and compare it with your corrected spectrum. For this case, I do not have the uncorrected spectrum, so I cannot show it, but you will realize that these error bars are going to be much, much larger with 1% uncertainty. So what happens is that RXTE is kind of detecting, but as you can see, the energy bins here are much larger than your XMM Newton spectrum, which means that for the energy levels between I think that's 6 keV, let's say 5.8 to 6.2 keV, it will only give you 2 energy bins, while XMM Newton will give you, I don't know, 5, 6 more, so that you can actually have your absorption components much stronger than your RXTE, which will also give you much better precision when you want to assess the width of this absorption line, which will tell you, I mean, we're not going to be doing it, but this width will tell you how fast your accretion disk wind is moving towards the line of sight. So at lower energies, as you can see, there are some wiggles at between, let's say, below 2 keV. This is not really that easy to see from this, but from my analysis and my search through the literature for GRO J1655-40, these observations actually coincided with the presence of a dust halo around GRO J1655. So one quick addition will be just adding one component to your spectrum. I will add it before the constant because I want to see the constant always up front. That's my personal preference. So which means that I will need to put the component between constant and TBFs. I will say 2, and it will be called dust. So this is basically the fraction, and this is the size of the halo. And I will just quickly hit it like this, and you will see before starting to fit, it's better to take a look whether or not these parameters are frozen in your new component or not, because for some reason, sometimes people actually freeze these to certain values. So it's better to check them beforehand. For them, I need them to be free. So instead of just, having to free each parameter one by one, you can do it by basically continuously listing your parameter numbers which are basically these ones. These are model components. So you can see that this is just the number of components you have here. And here are the parameter numbers going from 1 to 8. In total, you will have 16 for the sum of your two spectra, but normally you will have only 8 parameters, which are going to be linked to one another like this. So I am freeing the parameters number 2 and 3, and I'm starting the fit again. Although it doesn't really seem to be doing that much of a difference. That's the point that we need to be concerned about, because the dust of the halo, the size of the halo is quite large. So I'm gonna say it should be something around 1. I'm telling this to the fit because it was 2 before we started the fit. Let me quickly show it to you. It was 2 before, which means that it's a reasonable size. And since we're still working with X-ray binaries, this is much, much larger than reasonable value. So I'm going to say, okay, let's start the fit from 1. And I'm going to see if actually it changes anything. And as you will see that it was reduced. That's the thing that I meant by finding the wrong minimum. So it was probably stuck in one of them and did not really find the exact parameter value that we need for the halo size. And this is basically the fraction of how much of your dust is being scattered. And if I want to plot it now, you will see that the lower energy levels where basically these points were at much lower values in the residuals that are not now shifted to your model, which means that they were absorbed by your halo, and now you're modeling them much better. So this also one other absorption, but physically it's not really certain whether or not this actually belongs to any physical processes happening in the disk or around it, or it's an instrumental problem. But for the energies around here, we know that this is an instrumental issue, and there will be some spectra that you will need to account for these differences. For this one, I will not be doing anything significant because this is not really that bad of a deviation. But my main focus here is going to be how to deal with this. Up until this point, does anyone have any questions or concerns or
yeah, one question.
Mhm.
I can't seem to get the first constant to froze. Be
you will
frozen.
okay, so you will just need to type this. So first parameter is going to be frozen at value 1.
Oh, okay.
So anytime you want to assign a certain value to
Yeah.
a number,
Okay. Yeah. Yeah,
you
I
just say,
understand it now. Thank you.
okay.
I
So
was.
let's, okay. Everything fine now?
Yeah. Everything fine.
So we know, we see it now from our residuals. Now we want to take a look at what the values are for our parameters. First, start comparing the constant factors, which means that basically are just, you can interpret it as a normalization factor. You will see that this is very, very close to your value that you set for XMM Newton, which means for this specific observation, both spectra are pretty much similar in terms of their overall count rates. The difference, as you will see, are actually becoming much more stronger at higher energies, and that's why you will see a little bit of difference here. But considering how well they align over here, it's actually very nice indication. And you will see that this number is actually, okay, this is a very small number, but for absorption, this is kind of high, which also suggests that suggests a theory that there's another absorption column along the line of sight. And then you see your accretion disk temperature. And this is the normalization, which indirectly is correlated with the inner edge of the accretion disk. I will quickly show you how the calculation is done. If you don't know specifically, like any specifics about your model, you can basically Google the name of the model and type XSpec next to it, and it will give you some website with a symbol like this. Here you can have whoever actually started this, although this is not the exact description of the disk model that I'm using now. It's a very simplistic Shakura-Sunyaev accretion disk, non-relativistic. So if you already know how the temperature and the inner disk radius are related in the prescription itself, then you don't really have to go and look at it this way. It's basically the same. So in terms of the normalization parameter, it is usually scaled by the count rates that you have in your spectrum. And it also is indirectly related to your Rin in here. So this will be, if you are interested in the Rin components of your accretion disk, you can use it. But if you remember the seminar that I gave in November, this value will be unrealistically low, lower than the ISCO for your specific black hole spin and black hole mass. So this will be given in terms of kilometers. So what you will have is going to be in terms of kilometers, and that will be very, very low. But if you want to have like some sort of an assumption, then you can use it. Here it's the inner disk radius in kilometers. This is the distance in the units of time, kiloparsecs, and this is your inclination angle. And it's also good that they highlighted this is an apparent inner disk radius. But yeah, this is basically it. If there is anything that you don't know about a model, or you want a better description on how certain parameters are calculated, it's a very good practice to just go and Google. Like if there's anything I learned from my PhD, is just go and Google. Here you also have your power law photon index and the normalization of your power law. As you can see, this actually corresponds to a quite flat power law, which makes sense judging by the spectral shape over here. But if you want to make sure that this is actually the exact, oh no, it's not 5, 7. This is the exact value that you are interested in, you can basically run your errors, and as you can see, it basically gave out the error value with a confidence range. So this corresponds to 90%. I'm hoping that there's going to be one parameter that I can show you how the better fit has been found. So I'm going to run error for the whole set of parameters from 1 to 16. So unfortunately, it did not find a different fit for our case, but there will be times where you will see a new best fit found, changing the parameter values to that result. So this is a simple power law. You can play around with different power laws. Let's say I'm going to be quickly showing you the NTH comp example. Oh. So now you added your NTH component. You want to delete the power law component. This is done by del comp, and you give the number 6, and now you don't have it anymore. Let's see what the parameters are. This is your gamma, the photon index. This is the temperature of your electrons in your corona. This is the temperature of your black body seed emission from the accretion disk. This is basically a switch whether you want your input spectrum to be described as a black body or a multicolor black body. So I will keep it at 0 because this is basically assuming that it is a black body, not a multicolor black body, just for the sake of it. And this is the redshift. And as long as you are not working with, high redshift sources, you don't have to worry about it. Most of the black hole X-ray binaries are galactic binaries, and they will be very, very close to us. So this can be kept at 0. As you will see that this parameter has to be free. You will say the parameter 9. And as I mentioned before, this parameter has to be tied to your accretion disk temperature that you have from disk BB. Checking from here, it means parameter 9 is going to be equal to parameter 5. We do this with the new par. Parameter 9 is equal to 5. And now you want to see if you actually did it correctly. Your 9 parameter is now your 5th parameter. All right, you are technically ready for another fit. You see that your chi-square value is lower because you have a different number of free parameters in your total model now. And let's see what we're going to have. So your gamma value is also a little bit lower. You can see that this shift actually happened across the entire spectrum because it takes your accretion disk emission as an input. So it also is modifying things around a little bit. I'm gonna just run quickly an error on parameter 7. Okay. So this basically is your actual parameter value, and there's nothing else you can do about it. For this specific spectrum, let's keep the power law component at nth comp. One teeny tiny problem with power law is that, as you've seen, it is just 2 parameters. One, the normalization, which is basically telling you what your count rate is for your spectrum. And the other one is just gamma, which means it's basically just the slope of your component. So if you start plotting your power law component with just one slope, it will be going to infinity at lower energies. So you want to avoid that. And it's also very unphysical because if you want to compare the disk contribution at lower energies to the contribution from your power law, then your power law will say, okay, but the power law is going to be higher over here. So it's always better to have physically motivated power law models like nth comp. There are also a few other ones if you're interested in, we can try them out later on. But now I want to continue working with this nice feature. Do you have any questions up until this point? Or am I even going fast for you? Please let me know.
Probably okay, but I can't seem to reduce the chi squared.
What is your value?
986.
Did you remove energy levels?
Yep.
Can you share your screen with me?
Yeah, I can. You should be seeing it now.
Mm-hmm.
But I mean, I can't seem to know how to use the error function if it is possible.
Yeah, so for reduced chi-square values above 2, error will tell you, okay, your reduced chi-square value is way too high. You can basically continue typing after error. You can say max, and you can give, let's say, 100 for your reduced chi-square value. For you, it's going to be fine. So now you need to actually calculate a reduced chi-square value for a free parameter. Plus, you need to look at the KTBB in ATH-comp, which is frozen at 0.1. And for our case, that it should be at 1.2. So
Okay,
that's probably why
so-
you're having your.
So I need to set it up. Okay, I need to find the, how is it done?
So I can tell you now if you want, so we don't waste any more time and
Yeah,
see.
okay.
So you can just say new par 9 equal 5.
Okay.
Yes, hit enter. And now say show space par, show par. No, space in between show and par. So show is one comment and par
Yeah,
is
okay. Yeah,
what you want to see. So now check your ninth parameter is tied to your fifth parameter, which is your disk BB T in. So this should be fine. Now let's say if there's anything else. No, it's you need to also free the parameter numbers 2 and 3. You can do that. Yeah, okay. 2 and space and 3, and then hit enter. You can see again with show par. Yes, perfect. Now you see that those are free, and you also need to untie your parameter 13, which is the constant for your RXTE spectrum. So you can just say untie 13.
like this?
Exactly, and say 13. But I think it will, yeah. So you need to also unfreeze it by saying thaw 13. And let's take a last quick look. All right, it seems to be all right now. Okay, you can start your fit.
Yeah, that's
So
it's a better number.
Yeah, it's better number. So I reduced this data quite a while ago. So I might have used a different source selection, especially with the columns and everything. So to me, it seems to be okay. It seems to be okay for me. And okay, you're also plotting your spectrum. So as you can see in your lower energies of RXTE, that you don't have the same amount of counts as me.
You mean here?
No, if you go below what 7 kV, you can see that there are no counts.
Yeah, because I ignored them. Should I add them back?
Yes, please. You can say notice to double dot, however that is called, like you forget it. And without space. Without space.
5, 0 to 7.
No, you need to do it for 3 to let's say 10. Just say 10 because it will somehow not exactly match it. Okay, now if you plot it. That you will see now they're there.
Yep.
For the sake of our analysis, let's keep them there because it's also showing what RXTE is doing for us. Anyone else, any other problems?
Okay, so I will stop sharing. Thank you.
No problem.
Well, so far I'm just looking and listening, so I will do it later because I'm unable to do it as you speak. So.
Okay, I mean that's why I asked if I'm.
No, that's okay. So I will do it after that.
All right, but as in the case of yesterday, I will be online. So if you have any questions, you can ask them over Slack.
Okay.
So I will continue with the screen share right now. Right, I think this is the one. So we are back to what we want to do. Okay, I'm sorry, I'm gonna need to put myself onto not disturb right now. Yeah. So for RXTE, I forgot to mention, so I did mention the Xenon layers, but if you remember from your spectrum, Tomasz, that there were a lot of wiggles below 5 keV. So those wiggles actually are due to the, I keep forgetting this specific word, but it's basically because of Xenon layers becoming less and less sensitive to your high energy events. So it will basically start producing some emission features over here. There is a specific model to account for it, but it's better when you have a combined spectrum like this. You can basically ignore anything below 5 keV. So for this specific spectrum, I only have it above 5 keV, just to match at least one part of the spectrum together, and then continue with the rest. So this is going to be the focus feature that I want to address right now. It is so unless you are working with high resolution RGS spectra, which will show you tons of line features, and you can actually model them by different models. The easiest way to deal with these emissions is just add a Gaussian component. In our case, it will be placed between 4th and 5th model components at comp5. And this is basically it. The model parameters are the energy of the line, sigma of the line, and the normalization, which will actually tell you again the flux. But for this specific one, since we are not really dealing with emission, but rather absorption, as you can see, the normalization has to go to minus. So this will be just telling you from 0 to minus. And there's an easy way to define it. I will very quickly will say -1. And when you're working with defining your parameter from this interactive interface, let's say, you will keep defining different things. So 0, 1. And if you take a look at the values that you have here, let me extend it over here. These values will going to be your hard and soft minimum and maximum. What they mean is that you will first have your hard minimum. In our case, it's at 0. I will explain the difference between hard and soft. So these are going to be your minima. So it is set at 0, but we need it at -1. This is why I'm trying to show it to you. I will say it can go down to -10, even though it only goes down to -4 or maybe -5, let's say. So I will say both hard and soft minima are going to be the same. And for the maximum, it should be fine if you just give it 1 because it's an absorption line. So what hard and soft minimum means is basically when you are dealing with a parameter space, it's better to give a certain range for your parameters if you know them to be having that value. When I first showed you the halo size, and it was saying e to the +4, and I told you that that was not reasonable. It was probably finding the higher end to fit the spectrum. But if you cannot constrain the value that you are expecting for your model, but it is finding something different, then you can basically say, okay, wait a second, this is not correct. You have to be free, but within a specific range. Hard means it's a hard no. So you cannot exceed that certain value. Soft means it's a soft no. You can start your fit within first this soft minima and maxima. But if you really need to go above that limit, then you can explore between the soft and hard. I hope it makes sense, because the first time someone explained it to me, I was like, what? So it basically defines where your fit has to really stop exploring, and where it can't stop the exploration, the parameter space exploration, but it can, if it needs to, it can still go a little above that limits. So basically, for my case, I always define them to be the same. But if you're not sure about certain values and you want to give a little bit more margin to explore and find the parameter that you are interested in, then you can define different values. But this is done this way. It's you can actually see it from here that this is actually the higher number. So here, this is going to be your hard minimum, hard maximum, and these are soft values. And then I will just hit enter. And now it goes to the line feature for spectrum number 2. And I will just skip it, because for both spectra, while they have different number of bins, it will be still the same value. So it will need to fit both spectra at the same time. Before running the fit, I will quickly check what is happening here. So the line energy starts from 6.5, which should be actually somewhere over here. So and the minima and maxima are defined for a larger parameter range. And your sigma is at 0.1, which defines basically the width of this line. And then your normalization is going to be telling you that it's an absorption. And then I'm gonna start the fit, and fingers crossed, it did not do anything good actually, because I give the normalization maxima at positive value. So instead of doing it in the interactive case, as I just showed you, you can also do it like this. So this corresponds to number 9, and I will say 0.1. Sorry. So now I am saying you cannot go anywhere above 0, so it cannot have any positive values. And now you can see that the reduced chi-square value is much lower. And now I will plot and hope for the best that you will see that there's going to be a shift. And before then, you can see that the line energy is found to be at 6.9, which is exactly the energy for the absorption from your iron element that you actually want to see. And yes, as you can see that you are able to very well constrain this line feature with a simple additional Gaussian line, which acted both on your XMM Newton spectrum and also your RXTE spectrum. So why is our reduced chi-square value is not going to be at exactly 1? As you can see, there are a lot of features at lower energies in XMM Newton, and also some other feature over here at around 10. Physically speaking, there shouldn't be any physical process that might reproduce an absorption at energy as high as 10 keV. So it is easy to interpret it as an instrumental issue, but as you can see that it's actually present in both of them. But you cannot really tell what it is exactly. You can sort of account for these weird wiggles over here as an instrumental thing, but as you can see that the error bars are very, very stable when you compare it to your model. And the ones at lower energies, we know that they come from both a little bit of instrumental issues and also a little bit of your scatterings in your dust halo, which also be modeled by an additional component called dust. So as you can see, like certain values are actually remained unchanged, which is a good sign. Now let's say how your, I need to remove my earphones very quickly. So you should be able to hear me right now. Is everything okay?
Yes.
All right, perfect. My earphones were running out low on battery, so I have to remove them. So I will try to take a look at the total model. I mean, we are already seeing it in the solid line, but I want to look at how the components are changing with respect to each other. This is really, really hard to see, but as you can actually see that this is going to be your disk component. It's easier to distinguish over here. This is going to be your disk component, and this is going to be your power law component for RXTE. A few different things that you can try out with this is that you can try and give different values for different components and see where it is actually leading to. I'm gonna try to do it for parameter 6 and see which component is actually the disk component. You can also try coloring it, but as I also mentioned in the tutorial for XSpec and changing colors and putting labels, it's hard to know what component you are actually coloring it. It's easier for me at least to do it this way. So I will give for parameter 6, and instead of 1,000, I will give it 10,000. And now I want to see where it is looking, it is doing. Okay, ignore. I cannot really see the difference. Okay, maybe it's better to play around within parameter 5. So instead of 1.2, I will say, okay, let's do it 5 kV. So, okay, as you can see, the peak of this component has been shifted. So take a look at what it is doing like this right now. And when I complete the fit again, okay, as you also now see that it is finding a very, very different minimum, but I will fix it now, but just to show which parameter value, which model component that you're working with. And now you see that it is shifted a little bit. Let's check what the problem is. You can see that the line energy here is shifted to 75. I'm gonna say, okay, dude, remember what you found? It was 6.9. Let's start to fit from that specific value, but it is not doing it. I'm gonna quickly run the error for 7 to 9. as you can see, it is finding the fit. Yes, this is exactly what I wanted to show you before. So if you end up with a better fit when you run your error calculations, you will see this warning, which is actually a good warning. It will tell you that the fit found a new best fit, then it will start fitting the parameters starting from the value that it found. And then it will keep exploring the parameter space in a similar sense until it says, okay, I'm done. For our case, as you will see, as you saw, it actually ended up taking much, much longer, but it is still not finding the fit that we need. Let's see where the problem is, and we can see that the problem is actually going to be with the NTH comp. And you can see here the gamma is at 10, and it was 1.3, if I remember correctly, and I'm gonna say parameter 10 is going to be 1.3, restart the fit. It's still not doing very well with the line energy at around how many? 6.9. So you are actually experiencing it the first hand, how to deal with parameter degeneracies. So now you are seeing that you end up with the struggling with your line energies over here. For the sake of our argument and go back to the better fit values, I will just simply fix it to 6.9. I don't think it's doing, oh yeah. But as you can see that there's still a bit of a residual. It means that 6.9 was not really the exact value, but I can say, I can try and free it and then fit it a little bit. And I think now we are in the, yes, now we are in the safe zone. Any questions so far?
Not yet.
All right. Do you wanna, are you following the this procedure?
Oh, I am kind of. Right now I'm running my own error findings. So, but it takes a while. So
yes. So a few quick remarks about error calculations and everything. So the amount of time each calculation will take will depend on how complicated your model is, plus how your spectrum is. So it will basically mean that if it takes long and long and long just to get one error calculation, then it will tell you that the parameter space for your spectrum is way too complicated, and it is struggling to find the minimum and the maximum of your distribution, which is actually a bad sign. But it can also mean that it is just too much for the fitting algorithm. So because XSpec is not perfect, and believe me, I can talk about it for hours, days, maybe months, and maybe the rest of my PhD, how bad it is. But still, it is one of the best available tools we have. And we're gonna keep saying, okay, it's 90% good, only 10% bad, because certain, technical difficulties in the algorithm and everything. It's a very old algorithm, but it works very, very well. So it's not really how do you say it? It's not really that fair to attribute everything to your model and your data. So just to keep in mind, if your error calculation is taking way too long, like let's say more than 10 minutes or 15 minutes for your model, especially considering the fact that you are probably working with a newer computer, it shouldn't take any longer than that. If it does, reconsider your model. For this specific spectrum, this is very much okay, because you can see all of these features in XMM Newton. These are all features from the accretion disk. And you can see this feature very well even if you just take a look at your spectrum, you know that there's an absorption. But if you just look at RXTE, well, there's no need to even look at it. Like you cannot tell anything because it corresponds to only 2 bins when you can have 5 to 10 bins for your XMM Newton data. So if you continue fitting the same model to your RXTE data, then it's going to be a bit of an overfitting situation. We can actually try that. And I can also show you what overfitting actually means in terms of the statistics of the fit. So right now I have 2 spectra loaded. You can also see certain characteristics regarding your data files. So the net count rate means that you are observing, for this one, it's 98.7% of the total count rate for your region, which means that there was some subtraction from your background, which is good. For your RXT, it's also very good. You can also see all of these files loaded. You can see the time of your observation. For as you can see, XMM Newton was longer and RXTE was lower. If you compare these values to the values that you see for exposure time on either Hessar's archive or XMM Newton's science archive, you will see these values are different. And the reason for this is the selection criteria you apply when creating the good time interval or the GTI files in both instruments. So for example, for RXTE, in our case, we said only select the time intervals where PCU2 was operating and the source was, above the horizon and everything. So it was a specific time. So if you start including more PCUs, or if you say, okay, no selection, just give me the time, then you will match your total exposure time, which goes the same way for your XMM Newton spectra as well. So these are actual observation time that is being used for your spectrum. So when you're writing a paper, and if you are, for example, dealing with like pileup, and you want to calculate how many percentage of your net count rate has been excluded when you exclude the central columns, you can check these percentages over here. So what I wanted to show you is how to remove data. Unfortunately, it's not really that straightforward to remove one specific spectrum from one specific position, but in our case, we are kind of lucky that the RXTE spectrum is loaded first, and I wanted to just remove the PN spectrum, and I'm going to say data 2 none, I believe. Yes, the spectrum 2 is removed. We only have one spectrum, and I'm going to see. Yes, oh no. So it removed the spectrum 1 for some reason, but no worries. We can just say data. If you're working only with one spectrum, you don't have to specify data 1 to 1. You can basically say data 1 data, and it will already by default start from 1. And when you start adding PN, and then you will continue that way. All right, now we have one spectrum replaced, and I will continue with ignoring 25.5 and this. Let's plot it first. Okay. Okay. So here you will see that your reduced chi-square value is exactly at 1, which is not something I actually wanted to do. I was actually hoping it will be lower than your degrees of freedom, which characterizes the goodness of your fit. If your fit is going to, if your chi-squared is around the same as your degrees of freedom, which depends on the number of bins that you have and also the number of free parameters your model has, then it means you are actually finding your best fit model. And if your chi-square value is going to be lower than your degrees of freedom, it's going to tell you, oh, wait, there's something is wrong with your fit. It's not that your parameter values are very, very wrong. It's that your model is going to be way too complicated for the number of bins that you have and the number of free parameters that you have here. So you can actually start fixing certain parameters to certain values that you know that might have, or if you know, for example, from the fitting of XMM Newton, and you know that certain value has to be a certain parameter has to be at a certain value, then you can do it. For our case, as you can see, the Gaussian line has disappeared, and it gives a quite large sigma with a quite large energy level, which means it's probably trying to model the high energy tail. So I'm just going to go and quickly fix it to the value that we got from XMM Newton. Let's see. As you can see, degrees of freedom actually increase because now you have less free parameters, but your number of bins is the same. And then I'm going to start the fit. Here we are kind of in the lower end of your, it's still pretty, it's still 1. If you divide it, but then this is the point where your parameter space is kind of getting a little bit complicated for your model, for your specific fit. What you can do is that dust scatterings has to dominate at lower energies. You can basically start removing it, and this is done again by using DalComp2 and run your fit again. But unfortunately, the degrees of freedom is now increasing. So you have to be very careful with what you are doing with your model. And just show you again how the shift is happening. So the distribution in the bins, it has not changed, but some of them actually got shifted, but the pattern is pretty much the same. So basically, this is what I wanted to show you in terms of working with different instruments and how to choose which instrument you want to use for whatever reason that you want to do. As I mentioned in the first session today, RXTE provided an amazing set of observations for us to study the evolution of accreting black holes in X-ray binaries, and also other X-ray binaries. And if I remember correctly, RXTE even identified the longest pulsations ever observed from a neutron star. So it's like a huge set of observations that are still being explored. My entire PhD thesis actually depends on like 17,000 of observations obtained by RXTE when I was in middle school or so. So it's an amazing tool. But as you have also seen from how XMM Newton observation of the same source, the same day, not exactly the same time as you've seen from the exposure times, but the same source, the same day, actually is going to change the results that you have. Now you've seen from this, you can no longer constrain your line energy for your absorption, which you do not even see probably. I'm gonna quickly check how it goes. As you see, like you don't even see anything. So your absorption has to be happening over here, and you only have 2 bins. So it is important for when you choose an instrument to propose an observation, you need to consider the specifics of specific observatories when you compare it to the science case that you have. So this is actually going to be the end of the session. I will probably add a little bit more comments on the tutorial that I have on GitHub. because I now realize some of these are actually not listed in there. And I will also update, keep working on the PyExpect example. And if you have any questions or any comments.
I mean, not right now. Maybe, I don't know. I think that I got somewhere. I mean, I have like 374 chi-squared, so I don't think it's that bad.
It will depend on the degrees of freedom.
195.
Again,
So
it
it's
will
like double.
depend on your model components. So if, for example, for this specific case, I am showing you a model that I already worked with, but please make sure that you have all of your parameters free in all of the components. Like you need to have physical parameters like the temperature of your black body, the temperature of your electron, gamma of your power law distribution, the temperature of your disk again. These all have to be free. And if you see a reduced chi-square value that is way too high, then please check your model first. Then when you make sure that your model has all of the parameters that you're interested in, and also have to have free, that are already free, start looking at your residuals. And again, as I told you, we've probably defined different source regions when you extracted the spectrum. Unfortunately, I do not have exact same numbers in front of me to tell you what exactly I used, but it is possible that there are some differences between you and me when we extract spectrum.
Well, I am happy that I was able to get the Gaussian line energy to the point where I needed to. So
that's perfect.
That's my biggest like achievement.
I mean,
got it to
yeah.
the 6.93 and it's working. So yay.
Yes. So that is for an absorption line. And also, I will not get into too much of a detail, but as I also mentioned before, most of the times you might end up with emission lines in your spectrum. Just to quickly mention, the origin of them is going to be reflection, either from your coronal emission will come. I mean, so what happens is that your accretion disk starts emitting radiation, emitting light, which will then be reprocessed in your corona to be upscattered to higher energies. So let's say your initial temperature was 1.2, which means also the energy of your photon 1.2 keV, then it's going to hit a gas of electrons and it will be upscattered to higher energies depending on your coronal properties. And then it will be re-emitted from that gas of electrons. And some of these electrons, some of these emitted light or photons will hit back your accretion disk, especially if that the intensity of the emission is way too high. Then you are gonna start seeing more and more photons hitting back your accretion disk surface, and it will excite the iron elements that are present in your accretion disk, and then it's gonna start emitting energies in the rest frame, let's say, but it will be also affected and shifted by how close you are to the black hole, because the curvature of the space-time will define these energies, and also where in the accretion disk you are and how fast the accretion disk is rotating around how fast your matter is actually rotating around your black hole. So these will be affecting the actual temperature that you are going to be seeing. And most of the times your value will, so your emission line will lie somewhere between here. Say, yeah, somewhere over here. So instead of an absorption line at 6.9, which is not going to be that affected by the accretion disk and also the curvature of space-time, that's why we are seeing it close to the rest frame. You will see either a broad iron line, which will tell you this is originating from very, very close to the black hole, or sometimes if the corona is not just a blob that is hanging above the black hole, but it is an extended source, which will tell you that, okay, the corona can go up to the outskirts of the accretion disk, then it will get reflected again. Then it will not be as broad as you will see if it was closest to the black hole. So like there are also other contributing factors from this. So there will be some different reflection components that you can add. So most of the times for RXTE, at least, it's fairly easy just to add a Gaussian line. But also if you ask my supervisor, he will tell you a different story, and he will definitely tell you to start actually modeling the entire spectrum, because it will also give some contributions to the lower energies, some contributions to the higher energies in terms of Compton hump. So it's a different story. This is why I wanted to show you just how to deal with an absorption, because it's easy to model, because you don't really have to account for much of the physics that affects your disk emission and the relativistic reflection components and stuff. So you can just basically add your Gaussian line. You can also get your sigma, and then if you want to study the characteristics of your accretion disk wind, then you can move on and do other analysis that I'm not really expert in. So I hope I didn't really confuse you much more than I should have.
Okay.
Yeah. If you have any questions, again, I will be online over Slack. We can discuss it there. And if you want me to send you like some examples of the models that you want to play with, I can also do that. Otherwise, if there are no other questions, I will suggest we stop here.